So what are these specific crystal lattices? The particles in a crystalline solid will arrange themselves in a way to minimize their energy. And they will, based on their sizes and their charges, they will form different arrangements. And what we're going to do in lab this afternoon is we're going to actually play with spheres and balls and marbles and such and see how they pack together. So here is a sample arrangement, and if you were stacking, marbles in a box or basketballs in a box, this might be how they would work out. The first layer would go next to each other, and then the second layer would want to sit in that dip between two of the balls on the bottom layer. So when we look at a structure like this, we look for a unit cell. And a unit cell is the smallest unit of a crystal that when you repeat it in 3 dimensions produces the entire crystal lattice. So if we look at this purple square here, is that purple up there? It is. If we take this square and repeat it over and over and over again, we will get the crystal lattice. And which one is the correct unit cell is not always obvious. You might think that, I don't know what you might think. I'm not really thinking anything right now. You might try to draw different things, but then if you repeat those, they may not give you the same structure. So what we're doing here with the circles, these are the points of the lattice. That's where the atoms, the ions, or the molecules are. So that's the point, and then in between is some space. And we're not concerned right now about whether those are touching or not, but we're just looking at these points of the lattice. So if this was, say, iron, this would be an iron atom, and another iron atom, and each of these would be an iron atom. It can also happen with a molecule like sugar. Sugar forms crystals, right? Have you ever seen rock candy? It forms beautiful crystals. Each of these circles, these lattice points, would be a sugar molecule, and they would arrange themselves in a pattern. So this, in 2 dimensions, is a unit cell, but a crystal goes in 3 dimensions, and so we imagine this going into 3 dimensions, and it's actually a cube going back into the ones behind it. So the smallest divisible unit of a crystal that you can repeat in 3 dimensions to get the whole crystal lattice. When we're looking at the unit cells in this class, each atom in one structure is going to be identical to other atoms in that structure. So we're using colors just to help you visualize, but all the atoms are actually the same. So in analyzing these different structures, we look at the coordination number and the packing efficiency. Coordination number is the number of atoms that each atom is in direct contact with. And that is important because that's when 2 atoms are in direct contact, they're going to have the strongest interaction. So we're looking at how many touching neighbors does each atom or particle have. That's the coordination number. Packing efficiency is the percentage of the volume occupied by the spheres. So high coordination number usually leads to greater packing efficiency. There's going to be some empty space. You cannot pack spheres into anything and not have some empty space. That's just how they are. Now, cubes you can pack in and not have any empty space, but spheres, there will be some empty space. So something that has high packing efficiency, there's less empty space than something with a low packing efficiency. So here are 3 of the different lattices. So we've given them names. This is a simple cubic unit cell, and this is 4 atoms and they're stacked on top of each other. Okay, the actual unit cell, let's see, maybe if I use white. The actual unit cell goes from the centers of these. So the number of atoms per unit cell is actually 1, because this guy down here, 1/4 of him is within the box, and 1/4 of this one, and 1/4 of that one, and 1/4 of this guy, and 1/4 of that guy. And so there's 1/4 of each of those atoms that's inside the box, and that gets repeated to make the whole lattice. The coordination number here is going to be 6, because this atom is touching that one, and this one, and the one above. That's 3, and then there's one below, and there's one over here, and there's one over here. So it's actually touching 6. We can look at the length of the edge in terms of r, where r is the radius of the atom. And the length of this edge, it's half of this atom and half of the other atom. And so that's going to be 2 times the radius. And if we calculate the packing efficiency, we come up with 52%. That's the simple cubic. Body-centered cubic is where we've got one sphere in the middle surrounded by 4. And now they've kind of shown you in here with the light purple where that cubic unit cell is. So you've got the ball in the middle and 1/4 of each of these purple ones, and so that's a total of 2 atoms that are inside the unit cell. The coordination number is 8 now, because this guy is actually they're touching 8 instead of just 6. The length of the side gets a little more complicated, because now we're looking at a triangle and using the Pythagorean theorem to find this distance, because these guys are not actually touching each other. And the packing efficiency here is a little bit greater. So if you're packing basketballs into large bins or something, or oh, maybe you're packing stone fruit into boxes, you're going to get more peaches or pluots or whatever into the box using this body-centered cubic packing scheme. And that's often what they do. This is a face-centered cubic. So now we have, I think I've got some better pictures coming. You see there's 3 layers here. This layer has 1 yellow ball in the middle surrounded by 4 purple balls. The layer down here is 4 yellow balls, and they are in between these guys, and then the bottom layer is the same as the top layer. The result of this is that we get 4 atoms in a unit cell, and the packing efficiency now is even greater. So now that I confused you with that, let's look at bigger pictures. Simple cubic. So we took those 4 balls now, and we cut away so that we're just seeing the unit cell. So we've got 1/4 of this one and 1/4 of this one. And hopefully you can visualize and see that if we took one of these and duplicated it and stuck it right next to it, and stuck another one on top, and just made duplicates and copied them and stacked them all together, we'd end up with a lattice where we've just got purple balls in rows. So these atoms are touching along each edge. They're touching here and down here. And so when we look at the length of a side, it's going to be the same on all the sides. Here's the radius of the atom, and the length of the side is 2 of those, so it's 2r. There's 1 atom contained in this. I'm sorry, it's not 1/4 of each atom, it's 1/8 of each atom. I was thinking 2 dimensions. Any questions about that guy? Is this a quantum leap from what we talked about yesterday, or what? Yesterday we were all talking about intermolecular forces and stuff, and now we're talking about balls packing together. All in the same chapter. Excuse me. In this illustration, they're showing the balls spread out a little more so that we can actually see what's going on. But here's that cubic cell, the unit cell, with 6 balls, 6 at the corners. And then this would be another one over here, and there'd be another down here. And so we look at this guy right here to see the coordination number. How many balls is he touching? And there, he's touching 6. So that's the coordination number. And the packing efficiency is just over 50%. So there's a lot of empty space in there. Body-centered cubic, cutting that guy up. We see we've got this yellow guy in the middle. The idea here is not that the yellow and purple are different things. They're the same atom. We're just using color to help you see what's going on here. So this is the same kind of atom as the purple ones. We've just made him yellow so we can see him better. So there's one entire atom in the middle of this cube, and then we have 8ths of atoms around the corners. So all of those 8 atoms that we have 1/8 of will give us 1, and then the one in the middle gives us 2, and so we've got 2 atoms inside the cube. If you're interested, here's the math behind finding out what L is. And it involves a little bit of geometry. But the length of the side is 4 times the radius divided by the square root of 3. Now if we look at the coordination number here, focusing on this purple ball, we see that he is in contact with 8 other atoms. Higher packing efficiency. And the face-centered cubic. So here we see this is face-centered. We've got a half of an atom on each side and 4/8 of atoms. So we've got, well, let's think about that in the next slide. I'm getting ahead of myself. Again, here we need to do some geometry to figure out the length of a side. We can't just say it's 2r because this one is not directly touching that one. There's a gap in there. So we use angles and geometry to find out that the length of the side is 2 times the square root of 2 times, it's 2 times the square root of 2 times r. That r is not under the square root there. Coordination number here is 12. I guess they gave up drawing the lines to show that it's 12. But here we have 6 faces with half of an atom. So that gives us 3 atoms. And 1/8 of an atom at each of the 8 corners. So that gives us 1. So we've got a total of 4 atoms within the unit cell. And this has the highest packing efficiency. So chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium. What? Right? Okay. Body-centered cubic cell. So let's go back to that. It's face-centered, body-centered. So packing efficiency of 68%, that might be helpful. Length of a side, 4r over the square root of 3. There's no way I'm going to remember that. So the length of a side is 4r over the square root of 3. The packing efficiency is 68%. We're just going to collect these details and see how we can put them together. And there's 2 atoms per cell, per unit. So let's think about this. I'm going to write those things down at the top here. So L, white on white, it's kind of hard to see. L is equal to 4 times the radius over the square root of 3. There are 2 atoms per cell. And the packing efficiency is 68%. So we're told that chromium has a body-centered cubic cell. So there's a very sad-looking cube. The radius of a chromium atom is 125 picometers. So R equals 125 picometers. They're asking us for the density. We want density, which is grams per cubic centimeter. So to find the density, we need a mass and a volume, right? We want the density of the chromium metal, not of a chromium atom, because the atoms are going to pack together and there's going to be some empty space. So we're going to look at the unit cell, and how about if we figure out the volume in cubic centimeters of the unit cell and the mass of the unit cell? Could we do that? Yeah, we can, because we know that there are 2 atoms in a unit cell. Can we figure out the mass of 2 atoms of chromium? Yeah, it's going to be really, really tiny. We can figure out the volume of this as well, which is also going to be really, really tiny. And then when we divide tiny by tiny, we'll get reasonable. Right? Okay, so let's start with 2 atoms of chromium. 2 atoms. We have to do this in grams. So 2 atoms of chromium. And we want to get to grams. Well, we have the periodic table, which gives us 51, I think that would round to 52.00 grams. 52.00 grams of chromium is the mass of how many chromium atoms? 6. Avogadro's number of chromium atoms. It's the mass of 1 mole. 1 mole is Avogadro's number of particles. So 6.022 times 10 to the minus 23rd atoms. Thank you. It's not minus. I don't know. That would be really ridiculous. How can you have less than 1 atom? You can't. Sorry. Okay. So let's figure that out. 2 times 52 times nothing divided by 6.022 E23 equals. This is going to be negative exponent. 1.727. There's a whole bunch. There's several zeros after that, and then times 10 to the minus 22 grams. That's the mass of the cubic cell. The volume. What's the volume of a cube? The length cubed, or the length times the width times the height. So what we need to do is we need to take the length and cube it. So volume is going to be L cubed. Well, L is 4. Do you want to convert the picometers to centimeters now or later? Now. It'll be easier now. Where can we do that? Let's do that down here. I'll get rid of that dumb copyright thing. So 125. What I'm going to do is, instead of pico, I'm going to write what pico means. Do you remember what pico means? 10 to the negative 12 meters. And then I'm going to divide by meters, multiply by centimeters to get centimeters. What does centi mean? 10 to the negative 2. Oh. So I took 125, and instead of writing pico, I just wrote what it means to save a step. And then here I've got centimeters per meter, and it's 10 to the minus 2 meter. So I'm taking this number and dividing by 10 to the minus 2, which is going to get me 10 to the minus 10. If you do it on your calculator, it's going to be, oh, that makes my head hurt. (1.25) times 10 to the minus 12 centimeters. This is the form I got just by doing it in my head, understanding how to deal with powers of 10. And that is not proper scientific notation, but you can use that in a calculation. That is absolutely fine. If you punch this through on your calculator, this is what you're going to get. So we'll just use that one because people will probably be more comfortable with that. So we've got 4 times the radius, 1.25, times 10 to the minus 12 centimeters. That's divided by, oh, this is getting squishy, the square root of 3, and then we're going to cube the whole thing. So 4 times 1.25 EE12 minus equals divided by 3 square root of that equals, and then I'm going to cube that. And I'm coming up with 2.4056 times 10 to the minus 35 cubic centimeters. What do your calculators say? Same thing? So some calculators want you to put it in a different way. Are you getting a different answer?
Yeah, well, we did 125 times 10 to the negative 10. Wouldn't that be the same as 1.25 times 10 to the negative 3? Or
I don't think so. Let's see, 125 EE.
1.25 would be to the negative 8, yes.
What did I do? Oh, good grief. It's a good thing it's our Friday. Yeah, I screwed up there. Yeah, it was supposed to be 8. Okay, let's fix that. This is minus 8. And now that I'm looking at it, that's really stupid because, anyway, it is. Dum dum dum. Okay. Stupid can happen to anybody. Absolutely anybody. Okay, so then we don't want to mess around with that, so we'll just do it again. These are things that can be done in your head, but sometimes that just doesn't work as well as you would like. So now I'm getting to the negative 23. That's better, huh? Thank you. Okay, so we're going to put these numbers in here. Density is the mass divided by the volume. So we're going to take 1.7270, which would have uncertainty there, times 10 to the minus 22 grams. And we're going to divide by 2.4056 times 10 to the minus 23rd cubic centimeters. I'm getting, that would have 3 sig figs, right? 7.18 grams per cubic centimeter. Is that a reasonable density for a metal? Yes, it is. Metals are heavy. Metals are dense, right? Chromium, density of 7.18 grams per cubic centimeter. Any questions? So problems relating to these unit cells are going to require a little bit of thinking. And I was trying to show you how to approach this. Did that approach make sense? Let's identify the stuff they gave us. Let's look at what they want us to find. What do we need to find that? Let's get that together. So that was unit cells. Another way that we can envision crystal structures is to look at the layers, to think about the layers. And so this would be a layer here, and here's another layer, and another layer. So the simple cubic structure is one layer of atoms in a square pattern with the second layer lined up right on top of it. So this is forming a square, and it's lined up with the centers of the ones underneath. You see that? So if we're going up and down, they're lined up, and if we're going across, they're lined up, and if we're going across this way, they're lined up. That's the simplest structure, but there's a lot of empty space in it. We get more efficient packing by offsetting the layers so that this blue layer can sit in the little dips, the little holes made by the first layer. So by moving this over half of an atom, so instead of being right on top of this red one, the blue one is between two of the red ones. We take the layer and we shift it over. Now it's going to sink down, right, and sit in those indentations formed by the layer below. That's going to take up less space than if you've got them all stacked straight up on top of each other. So hexagonal closest packing is where you have the third layer aligned with the first layer. So here's your first layer, and then this second layer will be offset by 1/2 so it fits into the indentations, and the third layer will be lined up with the first layer. So this is called an AB pattern, where this layer and this layer are different, but then this layer is the same. And what would the layer underneath it be? B. And it would just go AB, 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 all the way down. So this is going to have a coordination number of 12 with a packing efficiency of 74%. The unit cell ends up being hexagonal. This is called hexagonal closest packing. So when we look for the unit cell of this one, it's not a cube. It's a hexagon. Doesn't that just make it all more fun? And so we've got 3 atoms in here, and half up and down, and then I believe there's 1/6 of each of those. Yeah, you just kind of have to stare at that for a while to figure out what you're looking at. This is that AB pattern where this middle layer is sitting in the holes caused by the first layer, and the second layer is lined up above the first layer. And then we have cubic closest packing. So there's layer A, and layer B is offset by 1/2 to fit in the indentations. But now layer C is offset from the first layer. See, this is 3 with the darker one in the front, and here there's a group of 3, but the point is going to the back. So this one and this, A and C, are not exactly the same. So this gives us an ABC pattern, a higher coordination number of 12, a packing efficiency of 74%. This is the same as the face-centered that we looked at earlier. So there's the face-centered, where we had a half on each of the 6 faces, and then the corners had 1/8 of a cube. But when we look at it in layers, here's layer A. Layer B is going to be offset from this. Layer C is offset from that. And then the next layer is the same. And so they took these 4 pieces together and set them on edge, and that's how you would cut out the unit cell. I'm just imagining that some of you are like, wow, this is really cool, and some of you are like, oh my goodness, I really, really hate this. It has to do with how your brain works and what you find amusing and not so amusing.